Good morning. It's a pleasure to be here, especially with this audience of so many people from around the world who have made the most significant contributions to our built environment. It's just a pleasure to be with you. Thank you, David, and thank you for all the fine work you've been doing with the Council on Tall Buildings and Urban Habitat. David said he was going to be really serious about the time. We had to stick to it, okay? So, David, just in case I don't respond to the bell, okay, I brought my own cane, and you're free to use it to get me off the stage. Thanks to my knee injury. Anyway, I'm delighted to be here to talk about the Spire. I was asked to talk about the technical things that were learned from the design of the Spire, the structural design of the Spire. And it was a real pleasure working on this project, and I just want to recognize the working with the developer, Garrett Kelleher from Shelbourne, and the architect and engineer, Santiago Calatrava, and coordinating so closely right here in Chicago with the architect of Reckitt, Perkins, and Will. And we had the pleasure of being the structural engineer of Reckitt. Get this thing going. So anyway, let's talk a little bit about the Spire. It's 2,000 feet tall, a little over 600 meters, and its circular twisting and tapering geometry was very successful in reducing accelerations and wind loads. And I think this is very important with all of the buildings out there that have different types of geometries. It shows a true integration of engineering and architecture to give you a most efficient building. Yet with the Spire, we wound up with a very straightforward structural system with the columns coming down almost perfectly straight, even though we had this twisting. But before we go further, I'd like to put the design within the context of a little history or evolution, as this conference is called. And there's been a quest for the most efficient structural geometries by engineers and architects for many years. Gaudi was trying to make spires that would not have the horizontal spread problem that domes had many years ago in developing some of his designs as shown here. But what he also accomplished here, probably not knowing it, with the combination of the taper and the combination of the circular design and the roughness of the design, it was an excellent design to minimize wind loads and wind accelerations, although obviously not all that critical on a structure of this height. And then as we got into the 70s and 80s, the council was doing an excellent job in trying to classify structural systems as to which ones would be the most efficient for different types of high-rises relative to their height. And the emphasis then was on steel, because there was this philosophy then that, go really high, you needed steel. But a lot of this applies to concrete also. And as we learned, as we went forward, that concrete had more and more advantages in high-rise construction because it's additional mass, it's additional damping, and the fact that as we got higher strength concrete, the stiffness went up also. So it became a great competitor to the steel. But what the council was emphasizing at that time they promised this would work as a pointer, see? All right. So I'm an engineer and I have my own pointer. So the emphasis was on the tube structure for going very high, okay, which had the advantage of utilizing all of the outside columns to resist the lateral loads and minimizing much of the bracing and sometimes eliminating it in the core, making the mechanical electrical engineers and the owner very happy. But it had very close column spacing on the outside. Now, if you notice here, they showed the typical, core with an outrigger, for buildings in the 50-story range. And the advantage of this design was that although we had bracing in the core, you had much larger spacing on the outside of the building. But one other little disadvantage is the outriggers had to go through and cause additional bracing inside of the core. So keeping that in mind as we go forward, we'll see what really happened. We started to realize with a variety of structures that the outrigger system could be used for very tall systems. But as I said, the emphasis then was on the tube, and it's a typical example of a tube structure here, which actually comes from the World Trade Center study, and it shows how for wind load in any direction, you activate all the columns to resist the wind load, and that's where you get the efficiency, and you also get a very high redundancy, as was shown by the excellent performance of the tube during the very tragic situation of 9/11. Then Chicago went one step further with the bundle tube. All of this was being developed at the time. The tube was basically invented by Fazl Khan from SOM. So the bundle tube got us even higher, but still we had close column spacing to concern ourselves with. But before the bundle tube, the John Hancock Center solved the problem of the close column spacing by giving us diagonals on the outside, a diagonalized tube, which was very efficient. As a sidebar, I'd just like to mention, when this building was studied, and you look at all the papers that came out on this building from, I think it was Hal Enger from NCON from SOM, you realize that these diagonals were not only helping with the lateral forces, but they were also helping bring down the vertical forces. So in many ways, this was kind of the beginning of this diogrid exoskeleton type of project that we're seeing. I just add that as a sidebar, actually. Then we started to use concrete more and more, as shown in the Kuala Lumpur project. And here, taking advantage of its mass, its damping, extra stiffness when you went to high strength, we were able to use a concrete core and then a framed core, but because of the concrete's massiveness in this frame with a relatively large column spacing, you are able to get a significant amount of tube-type action working together with the core. So concrete started to really come into its own, and it's been used in many other places in Chicago and obviously in Houston and places like that. But, steel was still competing, and the next tallest building after this was 101 Taipei, which was all steel. But concrete wasn't going to let steel get away with that. And now the tallest building in the world is interesting to note. Burj Dubai is essentially all concrete building. But getting back to outriggers for a moment to see the relationship with the New York Times headquarters. This building is basically an all steel building with outriggers. And typically the outriggers are every so many floors, and then they penetrate the core, which is somewhat of a disadvantage, but then they help bring back the building and minimize the deflections. But with the New York Times building, we eliminated some of the cross bracing on the inside of the building through the core of the outriggers and put it on the outside, thereby getting an outrigger type building with minimizing the interference on the in the inside of the core, making it a lot more MEP and owner friendly. So that brings us back to the Chicago Spire, and with the Spire, I'd like to just quickly explain the structural system in light of the evolution of structural systems. And I could add 3,000 more projects here to give a complete detailed evolution of structural systems. But that's not possible because of David's bell. But the Spire is basically a concrete core, steel structure, columns which essentially go straight down, some are at certain angles, and then the scalloped floor, which also helps in breaking up vortex shedding. The scalloped floor just twists a little bit, a degree or so every floor, and that's how you get the twist. And you can kind of see on this floor plate how each floor is just twisted a little bit. And that gives you this twist that comes down and gives you the architecture of the building. And it was Santiago Calatrava's way of wanting a design that he felt really represented both engineering and interesting architecture and minimizing wind forces. But one of the interesting things is that we have a concrete core, and what was developed was this circular outrigger. The circular outrigger picks up all the columns. By picking up all the columns, we get a almost tube-like behavior where all of the columns on the outside are participating in resisting the wind loads. And it's done in a way, think of it as a sleeve that's tight around the core. And there are no penetrations of the outrigger going through the core. And in this analysis figure here, the various different colors basically show that all of the columns and all of the outside are being activated to some extent, similar to the way a tube works, regardless of the wind in any direction. So I think the Spire wound up having somewhat of a tube-like behavior, and we got the advantages of that. Plus we had the outriggers allowing us, with a core, allowing us to have wider spacing on the outside. And we eliminated the bracing going through the core. So that was all fine and well. And then Santiago Calatrava said, you know, I really want to open up the lobby. And he had the columns had to come down, and we had to slant them out, go from 21 columns to 7 foundation pickup points on the caissons, which developed a whole new group of innovative ideas in other detailing for major connections. So there was a lot that was learned from that we think can be used on other projects. Okay. Now, the wind tunnel testing. I have about 5 more minutes. The wind tunnel testing was fascinating, the work we did with RWDI, and there was this back and forth looking at what the twist should be on the building from both an architectural point of view and from an engineering and wind point of view. So a lot of studies were done, and this is an example of one of the earlier models where you really get a sense of the twist in the spire. And we used 3 wind tunnel models as we went along, and we did a variety of different wind tunnel tests, culminating with an aero elastic test. And all of the models showed that with this twisting and tapering, we were getting loads that were about 75% of what would be required by the Chicago code. The models also showed, as we put more and more twist in it, okay, the second two models, the accelerations were significantly less compared to the accelerations of the first model, which had less twist at the top. But this very tall, slender building had an aspect ratio, no equations, just a couple of charts. Don't panic. Okay, this had an aspect ratio of about 12. It's quite a slender building, and it has a period of, for those of you who are into periods, it has a period of about 18, the time it takes to sway back and forth, 18 seconds. So what was very interesting with this project, at the 10-year return wind, which is the maximum wind in 10 years, which is the usual criteria we use for comfort, we were in the range of about 15, 16 millig's we use 1% damping. We were in the range that would not require adding any damping. And the large period was helping. But for such a high period building, what was happening, when we looked at the 1-year return, the maximum wind in 1 year, and the maximum wind every month, working very closely with RWDI, our wind consultants, it was determined that we felt that this was pretty high for getting something like 7 millig's to 10 millig's that would happen maybe every month or just once a year. And that's because of the very high period of this building. You can start getting unacceptable levels at lower speeds. So it was something else that was learned, and that gets aggravated the accelerations get aggravated if you have high vortex shedding, which gives you a resonance. And just a little reminder what the vortex shedding is all about. And this one little curve, just pay attention because it's really very interesting. Okay, what this shows is that at the lower wind speeds, okay, the lower wind speeds that I just talked about, we were getting more vortex shedding than at the higher wind speeds. And the other thing that was happening that's interesting, building has mode shapes, everybody knows that, and typically this is the first and second mode shape. That's just your normal sway of the building. And most buildings, 99% of the buildings, that's all you have to consider when you look at the dynamics of the building. But something to be learned here by everybody, with a building of such a high period, and we're seeing more and more buildings with high periods, as you know, the second and third mode shape, which was this kind of swiggly thing here, was contributing 20 to 30% to the accelerations, which means if we have to put a tune mass damper in the building, which we had to for the lower wind speeds. Remember, we put a tune mass damper in for the lower wind speeds, not the higher wind speeds. If we have to do that, we have to address both of these mode shapes to minimize those accelerations. So RWDI did a wonderful study where we looked at tune mass dampers, but the problem was that a tune mass damper can only handle one period at a time. So to do that, to do these third and fourth modes, we would have to have tune mass dampers not only on the top, but we had to find some other places in the building for it. So another thing that was learned, looking at all the economics and everything, we went to an actuated mass damper, okay, which senses the building movement, senses what's happening, and can move the damper in a variety of ways to handle all the modes just by using one one damper. So I think we're going to see more of this type of thing as we go forward with buildings. And the last thing on the wind loads is not everybody was really going to believe us that at these lower milliges, like the 7 or 8, 10, okay, that you really had a problem. So we did the first simulation at a motion simulator in Newfoundland, which is usually used, excuse me, my lips just got a little dry, which is usually used for ship motions, okay? And people went down to this, and the simulator is all programmed to move like the building with actual views of the Chicago skyline in there as you go up. It simulates you going up to give you that whole sense, and there's a place to sit and everything. And then there was a variety of different approaches that were taken, a variety of different scenarios. And yes, we had people there who were not technical, and they felt pretty uncomfortable, okay, when the tune mass damper was off in the simulation for the 1-year returns and the 10-year returns. Okay, but when the damper went on, they felt very comfortable. And this, to our knowledge, is the first time this has been done. And I think there's something here that could be utilized in a lot of other people's projects. So, in anticipation for the bell, I have 2 more minutes. 2 more minutes. I just want to quickly show you what's out there now. A lot of work has been done on the foundations. We're at the north inlet of the Chicago River, where it comes out of the Lake Michigan. We're surrounded by water here. There's a slip up here. We got Lakeshore Drive here with foundations, and we got condos on this side. And that's a view of the cross section. And basically, there are deep caissons. In Chicago, we very often for high-rise buildings, you use deep drilled-in to rock caissons, and then you use belled caissons for the not-so-high-rise buildings. Let me just say that for the benefit of this presentation. And the site had a combination of a slurry wall and drilled pier, and then to expedite construction, there was a cofferdam here, so you can start building the core and putting those caissons in, and then doing that at the same time as you're doing the wall all around, and then eventually use the top-down construction, just a three-dimensional view of that. And this gives you a feel of what's out there. We got the slurry wall. This is all in. This is all in. These are old, actually, now. There's that cofferdam I talked about. All right, 10-foot diameter caissons drilled in. And then we use top-down construction, which, if anyone here does not know what it is, it's basically you put in the slab, you dig a little bit, okay, and then you take it out through a hole, all your waste, and then you put in another slab below, so you're constantly using the slab you're building to hold back the site, which is a very efficient way of minimizing movements around the site, which really had to be done here. This basement is 7 stories deep, and to my knowledge, it's the deepest basement that's been done in Chicago. So that's the status. All the foundations are in, and I'll just close it up with this picture. That's the current site, and we hope that site in the near future will have some degree of vertical images in it. All right, thank you very much.